So, so please listen. So if you have any doubt while explaining, you can ask me at any time through chat box, or you can unmute yourself and you can raise a question. Now the optimizer that I am trying to explain today, that is called as the momentum optimizer. Momentum optimizer. So before going to the mathematical part, we will discuss about the background scenario. Why we are coming with a momentum optimizer. Let's consider a convex objective function. Let's consider a convex objective function. So let's assume this is the decision variable x, and this is the objective function f of x, and my objective function convex. So it will be like this. It's like a bowl, or it's like a valley point. It's like a valley point between the two mountains. It's like a valley point. So generally, in case of the, see, everything is a variant of the gradient descent algorithm only. All the algorithms which I am discussing in the complete FDP are the variants of the gradient descent algorithms. And these variants are popular and used in the machine learning and deep learning training process. Okay, that's why I told that it is a basic training program, basic workshop, or basic FDP. It will be helpful to the people who want to learn machine learning or deep learning further. So now, in case of the gradient descent algorithm, what is our first step? We are generally come up with some random initial point. Later, we are updating this point slowly as iterations are progress, and finally, this point is trying to reach this global optimal point or valley point or the peak point. Okay. Now, I said earlier, impact of eta. So that means you are able to see some oscillations. You are able to see some oscillations around the valley point or the bottom point or the optimal point. So I want to consider this one with a small case scenario. Let's assume, like you are randomly initializing a point. Let's assume at that point you are keeping a ball. You are keeping here. Okay. And if you leave this ball at this point, then what will happen? It will move towards and trying to reach this bottom point, right? When you leave this ball at this point, you can consider it as a bowl. It's a convex function if you see it as a mathematician. Otherwise, you can see, so it's like a bowl. So if you release a ball here, like a initial point, if the initial point starts here, in order to reach this bottom point, if your initial point starts here, in order to reach this bottom point, then tell me, if you release the ball here, ball is nothing but your initial point that you initialize for your model parameter. If you release this ball here, then what happened? It is coming down because of its gravitational force. Do you think the ball will struck here? It will stop here immediately? If you release the ball, do you think it will stop here immediately? No, because of the gravitational force with some velocity, it's coming downwards towards its optimal point. But it will not stop immediately here because of its momentum, because of its velocity, because of its kinetic energy. Then what happened? It may move further toward the negative slope side and coming back to the positive slope side and oscillates, and finally stabilize at that optimal point. That's what happened, right? Okay, well, let's assume you are releasing a ball here, and because of the gravitational force, it is coming in the downward direction toward the optimal solution. But once it reaches the optimal solution, don't expect that ball will be stop here immediately. The ball will be stopped here immediately. No, it will move further slightly in the negative slope direction also because of based on its kinetic energy or momentum or with some velocity. And later it is coming back to positive and oscillates around this point, finally stabilize at this optimal point. The same scenario will be happening in the model parameter updation also. Model parameter updation also is coming toward the optimal point. And even though you are choosing this learning rate very small, but sometimes there is a possibility of slight oscillations around that point. Now we are going to avoid those oscillations around the optimal point. Now our main goal is we need to stop the oscillations around the optimal point. Okay.
என்ன கிரேடு?
So please mute yourself. And if you have any questions, you can unmute. And first of all, please, sorry, I forgot to ask you initially. Is my voice is clear, right?
Yes, sir.
Yeah, thank you, madam. So, okay. So, coming to this scenario, so if you release a ball here, okay. Okay. So if you release this ball here, then it will be coming toward the optimal point location because of the gravitational force, but it not stop here immediately, but it will oscillate around that point. Similarly, same thing will be happening during our model parameter updation also. So even though we choose the small area, there is a possibility of oscillations around this point. There is a possibility, but very less possibility. Now, how we will avoid these oscillations? How we avoid these oscillations, and it will be coming slowly toward the optimal point. It will be stopped here. How we can do that one? So generally forget about the optimization, mathematics and everything. Suppose a big object is falling from this point toward the valley point. Now I want to move this one slowly toward the optimal point. I want to, once it reaches this point, I want to keep it stopped. Then what we can do, what is our solution? What we can do to get that situation? If you release a big object, and a big object, if you are releasing here, so it falls in the downward direction, it will come here, but it oscillates around that one. But I want to avoid that oscillation. Then what we will do? We need to apply. So let us do maybe a person who holds this ball in opposite force, and slowly it is coming down, and he will apply opposite force not to move very fastly, and finally it's coming down along with that boy or girl, that boy. So finally, once it reaches this point, because of it's coming with slow velocity, very less velocity, so that once it reaches this point, it will be coming to it will be stable at this point. It will be stable at this point. So I can give this explanation very well if we are physically in a classroom, but I think you are able to understand this as a case study. So if the ball is released immediately, then it will coming with very fast because of based on the gravitational force, and with the high velocity, it will oscillate around that point. Now I don't want to see these oscillations. Once you release this point, then we have to apply an opposite momentum, opposite force we have to apply. And this opposite force should be, because of this opposite force, the momentum of this ball or the velocity of this ball will be reduced, and so that it will be coming slowly. And once it reaches this bottom point, it will be stable without any much oscillations. Okay, so it's clear, right? I think it's clear. So in order to avoid the oscillations, what I am doing, whatever the initial update is there, for that update I want to apply some opposite force. With some force it is coming downward, I am applying some opposite force to that one, so that the updation will be slowed down, the velocity will be slowed down. That concept we are applying in the momentum optimizer. That concept we are applying in the momentum optimizer. So what if you forget about this man, so it will update normally as per the gradient descent algorithm. But in order to reduce the velocity and in order to reduce the oscillations, I am trying to apply some opposite force, some parameter which is opposite to this updation, so that the updation will become slow, the velocity will be slow, so that it will be coming slowly toward the optimal point, and it will be stable at the optimal point without going toward the negative slope. Or if it starts from the negative slope, it will not go to the positive slope, it will be stable at the zero slope point. It will be stable at the zero slope point. So that is the advantage of the momentum optimizer here. Right? So I think it's clear. So how we can incorporate mathematically this scenario? How we can incorporate mathematically this scenario? Tell me how a model parameter can be updated. We know that m equal to m plus delta m. That's equal to m. What is the delta m value? If you remember, what is the delta m value? the gradient method only, but some variants. So delta m value, what the delta m value? Or change in step length. Step length value, that is the minus eta into
Eta.
dou E by dou M. So this is m minus eta into dou E by dou M. Okay. So this is the actual value and this is the step length we are adding in one direction. This is the with negative, we are applying some update to our original parameter value. Now that what I have. So in order to maintain the velocity slow, to make it slow down, I am trying to apply some force, some momentum opposite to this one. So because it is the minus, I am adding some parameter with positive. So that parameter is gamma into some velocity Vt minus 1. So Vt minus 1 means it is the velocity factor in the if we are in the current iteration T, then we have to take the velocity of the previous value. Just listen carefully. You can get clear picture once we are going to the algorithm and calculations part. So what happened? So this is the negative and this is the positive. So that means one is in this direction and another is in opposite direction. So that the next update will be slow down so that there is not much oscillations or no oscillations much at that bottom point, at optimal point. So this is how we can update the model parameters. So this is the m equal to m plus, this whole term is called as the velocity term. So m plus Vt. Vt is the velocity term in the current iteration is equal to what is the Vt value? So Vt value is equal to gamma into Vt minus 1 minus eta into dou E by dou M. So this is what velocity factor is, velocity parameter is. This is what velocity parameter is. So this parameter will help to update your model parameter. Try to remember this expression very carefully. Right? So that's only change. See, I think you are able to understand here. So actually in our previous case, this is the only parameter, but we are adding some opposite parameter. The update is not much faster, so that there is not much oscillations in the bottom point, at the bottom point or at the optimal point. That is the only difference when compared to the previous one and compared to the momentum optimizer. In the momentum optimizer, we know that the eta value equal to learning rate. This is called as the learning rate, and whereas gamma is called as the, what is it called, gamma? So gamma is called as the coefficient of momentum or momentum coefficient. So this is called as the coefficient of momentum or momentum factor or momentum coefficient. So right, so this is that you have to understand. So based on this Vt value, we are going to update the model parameters for every iteration, for every sample. So that's happening in case of the momentum. So only thing you have to understand what is this parameter and we are using this one. Why we are using this one. Right? So now you can see, for example, I'm saying we are in the first iteration. Let us assume we are in the first iteration. So when the first iteration is, let us assume t equal to 1, first iteration. Then what about the m updation? So m equal to m plus gamma into V naught minus eta into dou E by dou M. So V naught is the initial value. That means previous value. Where in the first iteration means previous value means initial value. Dou E by dou M is nothing but gradient at that iteration. Gradient at this iteration. So this is the gradient at the t equal to 1, where V naught is previous value. Okay. So this is the previous value. So we can write it as a m plus V t equal to 1, V1. So where V1 equal to, what mean by V1 equal to gamma into V naught minus eta into dou E dou M. So please carefully observe here. So this is corresponding to the iteration 1, whereas this velocity, this parameter is from the previous iteration. Let's move second iteration. Let us assume we are in the second iteration. Then what happened? M equal to m plus gamma into what it will be? V1. Because t equal to t minus 1, previous iteration, that means V1 minus eta into dou E by dou M. Dou E by dou M, and this is for the current iteration, second iteration. Okay, and this whole part is called as the V. This whole part is called as the velocity term in the second iteration, Vt, right? Vt, t equal to 2. So V2 equal to gamma into V1 minus eta into dou E by dou M at the current iteration equal to. Right? Clearly observe here, please. So how I am representing this one further? M equal to M plus this whole part can be written as a V2. Okay? Now clearly observe. So this part, this negative part, this part is corresponding to the current iteration. This part is corresponding to the current iteration, current slope. And whereas this part is based on the V1, right? V1 is coming from where? Previous iteration slope. T equal to 1 slope or T equal to 1 gradient, V1. And in the current iteration, this is the gradient. Okay. Now your updated value V2 value, your step length V2 value or velocity V2 value is depending upon gradient or slope in the current iteration, and also V1 is nothing but the gradient in the previous iteration or slope in the previous iteration. Okay. The velocity value or the update speed with which your point will be updated, it depending upon the two factors. One is the gradient or slope in the second iteration, current iteration, and V1. V1 nothing but it is depending upon what? Gradient in the previous iteration, right? Or slope in the previous iteration. You can see here. You can see here. V1 is depending upon the slope in the previous iteration. V2 is depending upon the slope in the current iteration, right? Slope, this is the slope in the current iteration, and V1 nothing but the slope in the previous iteration. So now see how it will be happening. If the both slopes are current slope and previous slopes are, both slopes are positive. If this is the positive and this is also positive, then your VT will be larger update in the positive side. Okay, because both are adding. If both are negative, so then this is also negative, this is also negative, again it will be added but updated in the opposite side. But if is one is positive, another is a negative. If one is positive and another is a negative, then what happened? One is a positive, another is a negative, then net VT value reduced. Net VT value reduced means it will not go to here because of a reduction, it will be come here and stop here. Okay. So when the both slopes are same, positive, then step length is more. Both points are negative, both slopes, this slope and this slope, both slopes are positive, then the updated length is very large or speed is very large, and both are negative, then also speed is very large because both are added. Suppose slopes are -5 and -3, then it is a -8. If it is a +5 and +3, this is a +8. But if one is plus positive and another is negative, then the width will be reduced, right? 2. The VT value will be reduced 2. So that your width will be reduced so that finally it not go to the oscillation part and finally landed here. So that portion will be taking care here in case of the momentum. In case of the momentum factor, what we are incorporating here, that will help you to avoid the overshooting of the optimal point, and that also avoid the oscillations around the optimal point. How that will avoid the oscillations in the optimal point? As I said earlier, when you release a ball or optimal point, then it will be comes fast toward the optimal point because of based on its kinetic energy, based on its velocity. It will not come here and stop here, but it will go move toward the negative side and coming back to the positive side, and finally oscillate and will be stable here. That is the oscillations happening. Now I want to avoid those oscillations. I want to minimize those oscillations. Then what I can do? So instead of releasing freely, try to apply some opposite momentum, opposite force or opposite velocity to this ball. Then the updating speed of that point or velocity of the point will be reduced so that it is coming down slowly. And every time we are applying the opposite force so that once it reaches here, it will be stuck here, not move further toward the negative slope side. Right? So in that's the one thing. The second thing is, what happened to the updating speed? It always reduced? No. If your initial point is in the negative slope side, your previous point and current point in the what's called negative slope side, so both are added, minus 3, then it will becomes minus 8. Then your step length will be larger, but in one direction. If it both are positive, 5 plus 3, that is the 8, then maybe somewhere 5 and somewhere 3, then both are positive. So it also larger step length, but in the opposite side, is a minus and plus. But finally trying to reach toward the optimal point. But if one point is a positive, that means current iteration slope is positive. If the current iteration value is positive and previous iteration is a negative, then what happened when we are adding current iteration, previous iteration slopes? One is positive, another is negative, then what happened? Your step length will be reduced. So how it will be helpful? Suppose if you are somewhere near to your optimal point, so one point is here and another estimation is here. One is in the negative slope side, another is the positive slope side. So net value, when we are adding these two, the net value, net V1 value, net V2 value will be reduced. When net V2 value is reduced, V1 value reduced, so this V1 value is added to your point, right? As it is reduced, it is not jumping directly out of the point, but it will be jumps to the somewhere near to this point. That length will be reduced, the step length will be reduced because of the different slopes, one positive, one negative in the consecutive iterations. Okay. So this is what happening in case of the momentum. So if you understand this scenario, it's very happy. Please. Okay. So I think you understood these scenarios. So I'm trying to correlate the naturally what happening. I'm trying to incorporate that pattern to the optimization. I want to use that optimization for the machine learning model parameter update. So if you are able to understand this point, it's very fine. That will be helpful.
Can I ask a question?
Please, madam, please.
Yeah. This term minus eta d dm is always positive because of the minus sign, right?
That's depending upon
Because,
where our point will be, madam. Right now, suppose if you are in like this now, suppose if you are here at this point, so
slope
then
is
what
positive.
happened here? Slope is positive. That means dou e by dou m is positive, and we are adding negative this, it becomes negative. But if you are at this point, then the slope is negative and adding negative, so it becomes positive.
So increment is positive in case of the negative slope and positive in case of, okay.
Okay, ma'am. So suppose if you have any difficulty, suppose if you understand this one, for the faculty, it will be, I think it will be good to explain the students in the classroom. For the students also, it will be good. They can analyze the optimization algorithm very well. If you are unable to, of course, I'm explaining, I thought explained it clearly, but if make any confusion, you can ask me, I will explain once again. Even though it's difficult something to understand this slight natural scenarios, what I'm explaining, but if you're able to understand this equation is coming from here only. If you're able to remember or understand this equation, then you can write the code. That's enough. Now we will, I think if you understand this part, that is sufficient. So not only for this one, whatever the variants of the gradient descent algorithm, we are studying some new. If there is a small change, if you are able to understand that small change, then rest of things are same what we are doing till now. So we will, you are able to clear once you write the algorithm. Once we write the algorithm.
So do we want to reduce the velocity at every subsequent one?
Right, madam. So that it's not coming down fastly. If it's coming down like a same, madam, let's assume, madam, there is a very valley point between the two big mountains. And with a small bicycle, I'm trying to come towards the bottom of the valley point. Suppose if you're coming down, then I will coming fastly, and I want to stop at the bottom point, but I will not stop immediately because of that velocity, that momentum. It is coming to the So now I want to avoid that acceleration. Then what I can do? Suppose if you're applying some brake, regular brake means opposite force. So then it will be coming down, and slowly it reaches the bottom point very stably. That's what I am doing here. Just I am trying to apply some opposite force. That's it. Actually, we have only minus 80 into dou e by dou m, but I'm adding some opposite this one. And I'm updating the velocity. That is, I am adding to my factor model parameter.
If you're adding
Oh.
something, will that not increase the velocity?
One is similar. Oppositely, we are adding, madam. If one is a 5 and it is a 3, if you add both, it will be increased. If both negative, it will increase. Oh, I will explain once again otherwise. Suppose if you are here and if you are here, then we can increase the velocity, not a problem. But if you are reaching the global point and next point is in the negative slope, this point is the positive slope, we try to decrease. We try to decrease. So like it is a -3, it is a +5, then it will be 2. Here it is a 3, it is a 5. Both are positive, you can increase, not a problem. But in this case, we try to decrease velocity at this point. Otherwise, it will skip to there. So that's why I'm writing. So actually, we are adding Vt minus, see, this term you can see. This term you can see here, it is a V1. And this is the slope, actual slope. So this is called as, this part is called as the slope in second iteration. And this is the V1, right? So this V1 we are adding. And this V1 is coming from this slope. Sorry, the V1 is coming from here, this slope. Previous iteration slope. So that is the slope in the first iteration. If both are same polarity, then you can get the more Laplace, not a problem. If both are either negative, either positive, not a big deal. -5, -3, that will be -8, or 5 and 3, that will be -8, not a problem. But if you are near to the junction point where next will be negative, this one will be positive, in this scenario, we need to decrease that one. So then what happened? If one is positive, another is negative, then it will be 2, reduced, not added like this. So that is the change that incorporated in the momentum factor in order to avoid the oscillations and make to stable at the optimal point. So we are using this momentum optimal. So only thing we need to remember, that's it, how we update the model parameter. M equal to M plus velocity in this iteration, current iteration. So that is M plus gamma, momentum factor, into velocity in the previous iteration minus eta into gradient of that model parameter, gradient of that model parameter. So this thing we need to remember. If you're able to remember this thing, remaining part are almost same. So I think if anyone follow the last 3 days classes, definitely I'm sure you are able to give every step easily. So what will be the step 1? I'm writing the algorithm to update the simple linear regression model using the momentum optimizer. Now I will explain the algorithm. Later we will write the code. So anyone please, step 1. The task is, I want to write an algorithm based on the momentum optimizer to update the model parameters of a simple linear regression model during the training process. That's it. So now tell me what will be the first step if I want to write algorithm. As usual, initialization of our model parameter M equal to 1, C equal to -1, eta value, and number of epochs. Next, read the data, and also read the number of samples. What else? This is the eta, and this is the n, number of samples. So what else we need to?
Other constant also? Yeah,
right,
gamma.
madam. Right, madam. So gamma, so actually I said that eta value generally between the 0 and 1, whereas gamma value is generally between the 0.5 to 0.9. So this is how we will consider the eta and gamma value based on the multiple experiments. They suggested that is the range better to choose for the gamma value 0.5 to 0.9. So I am taking the gamma value equal to 0.5. Next. Anything else? N is the number of samples, gamma is the momentum factor. So next step is I think if you observe the updation of a model parameter, there is one more term is left. Velocity. So that velocity also we need to initialize. We need to initialize the velocity terms for every model parameter. Vm equal to 0 and Vc equal to 0. Why two velocities? One is for the m parameter and another is for the c parameter. So these two will be initialized because we are assuming that at starting our ball is stationary at that point where we are chosen. Later we are releasing, then velocity will be updated. That is the Vm0 and Vc.
Why are we separating Vm and Vc?
So we have the two variables,
While
madam,
we are
two model
writing in the
parameters.
algorithm.
Madam?
No, in the algorithm we talked only about V0 and V1.
And
Like
that means just I'm considering only m parameter. I am taking the only one V0, V1 like that. If you take m and c, we have to take the two different values.
Okay.
Now step 2, as usual. So that is the iter equal to 1, and step 3. So that is we are going to the first sample equal to 1, and step 4. Let us assume I'm taking the batch size equal to 1. For every batch size equal to 1 means for every sample I want to update the model parameter. Only for the explanation purpose I am consider sample equal to. So what is the next step? Anyone please? What will be the next step? Next step will be
GM value, sir.
that's it. GM value, calculation of the GM value. So GM calculate the gradients of each model parameter with respect to each model parameter. That's the minus. I think actual value ya minus m into x minus c into x. I think this is right. And similarly calculate the gradient g minus actual output value minus m into x minus c. So what may be the step number 5? What is the next step? Once you calculate the gradient, next what is the step of? Next step is, you can see, otherwise I will
Delta M and
otherwise see here, see how I can calculate delta m. You said that delta m. So delta m is nothing but with how much value you want to update the model parameter. That's what delta m shows. So with how much value you want to update the model parameter, that is the delta m shows, right? So m plus this is like a velocity is like a delta m. How we calculate this velocity delta m? That is based on these two parameters, right? You can see here. Vt is nothing but this parameter. This will be added to the m as a delta m or velocity. So we need to calculate this velocity. We need to update this velocity for the first iteration. So what we are doing here? Now what we are going to do? We have to calculate the Vm equal to gamma into previous Vm value. Already initialized there 0, 0 minus eta into Gm. That's it. No? Vt equal to gamma Vt minus 1 minus eta into dou E by dou M. That's what we are written in the previous derivative one, mathematical analysis. That's what same I am including here. Again, for the second model parameter, Vc equal to gamma into
Vm minus 1, right?
Madam.
Gamma times Vm minus 1.
Vm, but see, Vm equal to gamma. Vm is previous value it will take. Previous value 0. So that value it will take here. This is the 0 previous values. That 0 values are coming to the first iteration. These are the previous values. For Vm, I want to calculate the Vm value for the first iteration, for the first sample. But this Vm is coming from the previous value. Vm equal to 0 we initialized earlier. That value is coming from here. And Vc equal to gamma into Vc minus eta into Gc. So don't confuse why I'm taking the t minus 1 means I want to tell you previous value. That's why I'm taking the minus 1. So here also it will take the previous value. I want to update the Vm. So my new Vm equal to gamma into old Vm. Old Vm means 0. Previous value. Minus eta into and Vc equal to gamma into Vc minus eta into Gc. Right? So now,
Yeah.
after calculating the both VM and VC, so what the next step? Step 6 will be update your model parameter. So M equal to M plus VM and C equal to C plus VC. So like that, we are updating the model parameter. So next step number 7. So what is the step number 7? So it's like a gradient calculation. So same, previously it's like a gradient calculation. This is the step length calculation. This is the update. Same thing I am doing. So this is the gradient calculation. This is the step length calculation. And how much change we want to incorporate. This is the update. So these are the 3 steps only again. Only thing is the calculation of the step length will be changed in the momentum. And one new parameter is incorporated here. That is the gamma into VM and gamma into VC with opposite sign. So what next?
Sample increment.
Right. Same. Rest of things are same. Only change is here. That's it. So
Yeah.
sample equal to sample plus 1. So next step number is
If
what the
sample
step
greater
number?
than n.
Yeah, we are going to check whether all samples are covered from the data set or not. The sample is greater than n number of samples. So if it is a true or if it is a false, where to go, we have to think. If it is a false, where to go? That means your sample number not more than the number of samples in the data set. If that is the case, we are moving to the step number
Step 4.
4. Step 4. So if it is a true, we have to go to the next step. We have to go to the next step. And similarly, step number 9. So step number 9,
Iteration.
iteration. We are going to update the iter equal to iter plus 1. And next one is the step. So step number 10 is again checking for the convergence criteria. That is, if iter value is greater than epochs or not. If it is a true, where to go, we will discuss. If it is a false, where to go, we need to discuss. If it is a false, where to go? If your current iteration number is not greater than number of epochs that we define, then we are going towards the
Step 3.
step number 3. Again, go to the step number 3 and start from the first sample. If it is a true, go to the next.
Sir,
Sir,
this
please.
if sample greater than n, if it will go to step 4, no, sir, if it is true.
Step 4, sir. That's what I mentioned. True, na? Generally, sir?
If sample greater than n,
Okay.
it is going to next step.
Next step, sir. Iterations. What are our patterns are generally, I will explain, no problem. Data set, no, sir. So let us do this is the sample 1. This is the sample
Yes,
2.
yes.
Understood, no, sir? Sample 3, sample 4.
Yes, sir.
Hope you understand now.
Yes, yes, sir.
Okay, sir. So if it is in case of the iterations, if it is greater than the number of epochs, so then we have to go to the next step. There is the step 11, that nothing but the save your model parameter, and you can test your model based on these model parameters. Test your model, and check the error metrics, like errors like mean square error or mean absolute root mean square error on both training data and testing data. Save this model parameter. Calculate error metrics. That means both the training and testing error metrics. Yourself and your client all are happy with this training performance and the testing performance. Then you deploy this model into an application. Deploy this model into an application. So deploying a model into the application means just what are the updated model parameters are, take it back end of your application. Along with model parameter, you have to pass the architecture also. So that whatever the mathematical processing is required, that can be done in the backend. And finally, your application throws your final output. What you are going to predict, what you are going to estimate. So this is the complete flow of the momentum optimizer. Is the complete flow of the momentum optimizer. So only change is step number 5. As I said earlier, so every grade one algorithm to another algorithm changes how we are going to calculate the step length. That is the thing for change from one to another. So every researcher are trying to come up with some new strategy So like that, the many algorithms are developed, many optimizations are coming up, many gradient descent algorithms are coming up. Even after completing the course, training program, maybe we also think something novelty in this direction, because we know the mathematics, what happened behind. So you can come up with some novelty, some changes in your algorithm, and you apply the same changes for your machine learning training process, machine learning training. Then you can come up with some research articles, some novelty in the research article you come up. But you have to, if you don't understand what happened behind, every time we are using the dot fit model only. We are using the only libraries. We don't know, we can't enhance that model, enhance the algorithm. We are able to enhance the algorithm if you understand the mathematics behind the algorithm. So this is about the complete step-by-step algorithm for the momentum optimizer in order to update the model parameters of a simple linear regression model. So I think it's clear. So if you have any doubt in this, as of now, if you have any doubt in this algorithm, please let me know. Otherwise, I will try to write a MATLAB code first to update the simple linear regression model parameters using the momentum optimizer. So please tell me if it is okay, then I will move to the MATLAB implementation. Okay, fine. So I will move to the MATLAB implementation. I want to open a new file. I want to save this MATLAB file. So I want to write here as momentum underscore SLR underscore sample data. In class, I am demonstrating, so I am writing the sample. So this is my name of the file. So as usual, just I am following with CLC and clear out. Now please tell me sample data I want to use. So what is the next step? Anyone, please? What next step? So as base, or we can refer our step-by-step process also. Now, by referring this one also, we can come up what is our first step. Our first step is initialization, right? So initialize your data. So initialization means initialize your data. Okay. Our next step is initialization. Okay, initialization. So now what we are going to initialize? We are going to initialize random initialize M and C values. So that means I can define lower value equal to -1 and upper value equal to +1 and random initialize M and C. So M equal to lower value plus. I don't want to explain once again the logic behind here. Already I explained. So lower plus upper value minus lower value. That's how I am initializing the M. That's how I'm initializing the M. Okay. Similarly, I'm trying to initialize the C. So I'm trying to initialize the C. Okay. So what next step? We have to initialize our eta. I'm taking it the 0.1. And you have to initialize the gamma as a 0.5. And epochs, we can initialize epochs, that is the 1000. And we need to initialize anything else we need to initialize? MC, eta, gamma, epochs. Anyone? Any suggestion? What else I need to initialize? That is the M over C over eta over epochs. The epochs completed. And data we need to read. Number of samples from the data we can extract. Gamma 0.5. VM, VC we need to initialize. So VM equal to 0 and VC equal to 0. VM equal to 0, VC equal to 0. Now we need to take the data. I want to use the same data that what we are using earlier for same data I want to use. Okay. sample data. Yeah, this is the sample data that what we are using earlier. So I want to use the same data here. Now tell me, I want to extract the number of samples in the data. How we can extract the number of samples in the data? How we can extract the number of samples in the data? Anyone, please? Number of samples I want, n equal to, how we can get the number of samples in the data? That's equal to, I want to use size command of data matrix and first element that
One,
will be the number
yeah.
of rows, 1. It will give the number of rows. So I think all the parameters are initialized here. You can see M initialized, C initialized, eta initialized, gamma initialized, epoch initialized, and VM0 initialized, VC0 initialized, data extracted, data initialized, and number of samples also extracted. That's it. So all the required samples are collected now. So what next? So we have to start the iterative process. We have to start the iterative process. So for iterative process, we have the 2 loops. One is the iteration, and another is the sample loops. So what I can write for iter equal to 1 to epochs, right? For iter equal to 1 to n number of samples, and close this for loop and also close the external outside for loop also. Did I made any mistake here?
Sample. The
Right.
second line should
So this
be
is the sample.
for, yeah.
So sample equal to 1 to n. That's it. So now what is our step? Within that 2 nested loops, what we are going to incorporate? What are the steps inside? Between the 2 nested loops, what are the steps? Step number 4, step number 5, step number 6. Nothing but gradient calculation, VM calculation, updation. That's it. 3 steps only in every algorithm that changes. Gradient calculation, step length calculation, or here velocity calculation, or update your model parameter. That's it. So gradient calculation, now we can calculate the gradient. So we know that GM equal to minus, please, minus, we know actually, minus actual Y value, output value, minus M into input value, minus C into input value of that sample. So what I can write for getting the actual output value. So actual output is available where? So this is the data, right? So this is the data for me. So only for explanation, I'm taking the very small data sets. So this is the data, but actually in the real time, you required huge amount of data. In sometimes the samples may be in terms of thousands. Now, from where you got the actual output values in the data, that is the second column. So you can write data of, for that sample, take the second column, that is the output, minus M multiplied by X is coming from data of sample. X is nothing but input coming from the first column, mx minus C, and multiplied by, you can see here, multiplied by X, so that you can write here X is nothing but the data of sample comma 1, sample comma 1. That's the GM value. Similarly, GC equal to, so I want to copy whole part, Control C, and paste it here. And only what we need to remove, that X value should be removed at 10. Here how we can calculate the GM and GC values. This is how we can calculate the GM and GC values. Hope you understand here up to this point, right? Next. So next thing is, so after calculating the GM and GC, what we are going to calculate? Velocity update. So VM equal to, what we write, I think go to expressions. So what is the step number 5? VM equal to gamma into VM minus eta into GM. VC equal to gamma into VC minus eta into GC. Step length calculation, velocity calculation. So VM equal to gamma, right? Gamma multiplied by VM, that is the previous VM we had to take, minus eta multiplied by GM. That's it. This is about the VM. And now would calculate the VC. How we calculate the VC? Anyone, please? What modification I have to incorporate in order to calculate the VC? VM is completed. I copied the same line here, but need some changes. Anyone? To update the VC, what I have to do? To update the VC, what I can do? So VC equal to gamma into VC minus eta into GC, right? Gamma into VC minus eta into gradient with respect to the C. So after updating the VM and VC values, what we are going to do? So M equal to M plus VM and C equal to C plus VC. That's it. That's how the algorithm will work. That's it. This is the only the training. That's what happening. That's how your momentum optimizer helps to update the model parameter. Otherwise, you can write a comment in here. Process of momentum optimizer to update simple linear regression model parameters. So this is what happening here. Model parameters updates. Okay. So once the model parameters updates are completed, then what we are going to do? Just if you want, you can print your model parameters. If you want to see your model parameters, updated model parameters, just to print the model parameters like updated model parameters. Okay. So update model parameters are M and C. That's it. So save this complete code. Save this complete code and we can write M value, M equal to percentage 0.2F and C equal to percentage 0.2F. Okay. That I want to store this M value like here, and I want to store this C value here. M equal to something, C equal to something. Okay. Just simply save this complete code and you can run this algorithm. So this is what we are getting. Finally, M and C values are M equal to 2 and C equal to 3. Right. So once the training was over, you need to develop the application. Application is same as what we did earlier. So application development is nothing but you have to deploying a model behind an application is nothing but the just keep your updated weights backend of your application. So what are the updated weights? We know that M equal to 1.99, M equal to 2 and C equal to 3. So M equal to 2 and C equal to 3, right? M equal to 2 and C equal to 3. Next. What next? So we are giving a permission to the user to enter the what he want to expect. Suppose let us assume he want to estimate the value of Y and he will provide the value of X. So we have to ask the user who are using our application, we are asking him enter the X value so that I will give the predicted Y value. So X equal to, we have to use input and here we have to write enter X value, enter X value. Okay. So next, once you enter the X value, down you get the Y value. So to calculate the Y value, to predict the Y value by using your model, by using your simple linear regression model, you have to pass the architecture up. What is the architecture? Your architecture says Y equal to M multiplied by X plus C, MX plus C. That is yours, because we are taking simple linear regression model, that is the mathematical model or architecture of your simple linear regression model. And what next? So we have to printf, because finally your application will give some output, right? So predicted output or Y equal to percentage something 0.2F. In this space, that will be stored, the value will be stored, and that the predicted value will be available at Y. That's it. So this is how we can save the app. You can run the app like maybe momentum sample Yeah, apply to everything. Now, if you run this code, so it will ask you what the value of x. Suppose if I'm giving the x value equal to 0.2, and if you print enter, then it will give the predicted output value equal to 3.4. That's what actually our data also showing. If it is a 0.2, if it is a 0.2, and the predicted output will be 0.4. Suppose if you are entering 0.4, if you are entering the 0.4 value, sorry. If you're entering the 0.4 value, we're expecting the 3.8. Now for this application again run, if you enter the 0.4 value and we are expecting the 3.8, the predicted output value will be 3.8. Okay, so like that we can update the model parameters using the momentum optimizer. And once the model parameters are updated, and if you assume yourself, if I assume that myself and my client both are happy with my training and testing performance, then you can directly deploy your model in the backend of your application. So that's how it's working in a momentum case for the SLR updation, model parameter updation. Okay. Now,
When is the time when you split the data? Like last time we had used that function. Yeah.
generally, madam, that we have to do, but here we have only 2 samples for a explanation purpose. I'm taking very small data, but
Yeah.
generally in the real-time applications, we have the large amount of data. So once we have the large amount of data, we have to split the data for the training purpose. That means to update the model parameter. Once the model parameters updation is completed, to test the model, we have to keep a data separate data aside. That means the data which was kept aside for testing, that was not seen by the model during the training process.
Yeah.
Now, if we give that data, once the training is completed, once the model parameters are updated, so if you give some new data which is not seen by your model during the training process, if your model able to predict well for that unseen data also, then you can deploy the model in the application, real-time application. That's what actually we have to do. But here only I'm trying to write the code as per the algorithm what we discussed for the momentum.
Yeah.
That's why I'm not much concentrating about splitting of data, all the things. We will discuss definitely when we are going for the some real-time application. So for this momentum, as given in the brochure, I am trying to build a simple linear regression model. I want to build a simple linear regression model to predict the load on a substation at a particular hour based on the load available 24 hours back. So that case study I want to explain in case of for this momentum explanation. In that scenario, I will explain the all the things. I think we can do it in the MATLAB also. Yeah. Fine. So this is I want to stop here for the MATLAB case. Now we will move to the our Python. I think clear how I am writing the MATLAB code to update the model parameters of a simple linear regression model for this data using the momentum optimizer. So you can use the same piece of code with slight changes. Main change will be data. Here I take the very small data. In place of this one, you can keep your own data also. Then you can use the same thing if you want to use the simple linear regression model. The same code can be applicable. You can change the data. Maybe random data I have considered here. Based on your application, you can copy and paste here and try to run this code. Definitely, it will give the final updated model parameters. Fine. Now, I'm trying to explain the momentum, same sample calculation, sample data first using the Python, and later we will move to the load forecasting real time. Actually, the data which I am showing that I will show for this previous yesterday pH and bicarbonates case study. The data is coming from some online which is already available repository. And now for today's case study, I am trying to predict the load on a substation for a particular hour based on the 24 hours back load data. So actually, this data we collected in 2000. for our some BTech project purpose from the substation nearby our university. And that real-time data, with that real-time data, we will work on that problem. Okay. So for any machine learning thing, machine learning project, the main criteria is how you will be able to collect the data. Remaining things you can do if you have a good computing machine with you. Only thing is you have to collect the good data, you have to collect the real-time data, you have to collect the very good data. That means without any issues in that data, you have to find it. Otherwise, your model will learn in the wrong direction. You have to get the good data. Fine. Now I'm trying to explain the momentum for a sample data using Python. Again, I am using the Colab only. Okay. Sample data, that what we considered earlier for this SLR. Simple linear regression model, stochastic gradient, we consider one sample data, right? Here, as GD, we consider one sample data. So for this sample data only, I want to use momentum. I want to use momentum optimizer. Okay, please. Now tell me what are the things I have to do in the first cell. I will meanwhile, you can think what I have to write in the first cell. And meanwhile, I will give some title, momentum SLR, and it is a sample data. Tell me, so anyone please. So what is our first step? What is our first step here? So you can use Thoughtbox also. Yeah, please. I will share MATLAB code also. Please, I will share MATLAB code also in our group. Okay, fine. So now done. Okay. And now tell me what is the first step. So I think I showed the data to you, right? So this is the data I have. So I want to I want to build a simple linear regression model. I want to use a simple linear regression model so that that model is able to predict the variable y. The y may be a temperature or humidity, whatever it may be, based on some input value x. Okay. So what is our first step? So someone import, right? So we need to import all the libraries. So import NumPy as NP and import pandas as PD and import random initialization random and import what else we need to import one more I think you forget, right? Import math libraries as a empty. So just importing the libraries. So after that what we have to do? After that what is the next step? So we are imported all the required libraries. What are the required libraries? After that, what we have to do? Initialization, right? Initialization, right? So initialization means because it's a simple linear regression model. Simple linear regression model has the one input, one output. So that it has the only two model parameters, M and C. So you have to initialize M and C randomly. So M equal to random dot uniform, pass the upper boundary and lower boundary. And similarly, C equal to random dot uniform, pass the lower boundary and upper boundary values. What next? we have to initialize eta as 0.1, and we have to initialize the gamma as 0.5. And what next? We have to initialize the number of epochs as 1000. What next? We have to initialize the velocity parameters Vm for every model parameter. Vm equal to 0, Vc equal to 0. Anything else we need to initialize here? Otherwise, you can go to our algorithm. M, C, eta, epochs, data okay, this okay, gamma, Vm, Vc. I think everything initialized based on what we require. Okay, just simply run this code. This is the initialization showing some error. Anyone can tell me why error is coming here for me? What mistake I made so that I got this error? Anyone identified why I am getting this error?
Is that spelling correct? Uniform?
Yes, madam. It's the
Yeah.
spelling mistake. It's the uniform. That's why I'm getting error. That's over. Fine. So once the initialization is completed, what we have to do now? On the initialization is completed, what we have to do?
Data initialization. reading.
Data initialization, data reading we have to do. So let us assume data, or I'm writing variable, original data, that's equal to, from where we can get the data. So actually my data is available in an Excel sheet in my local file, local machine. So that I have to import the data from my local machine to this Google Colab framework. So for that, just click on this folder, and you can click here, upload, and where it is available, maybe role of optimization, SGD, practice, so sample data. So this is the sample data is available. Okay. Now copy this path. Now tell me how we can read this data. We can read the data from this Excel file and attach it to this variable. Anyone able to remember? Because we did this steps multiple times. That's why I'm asking. Already we did this one for the SGD. We did the same step for the BGD, and this is the third time we are using.
Panda, PD.
Pandas, PD dot, because it's the Excel file. So read underscore Excel. Read underscore Excel. So you have to pass the path. You have to pass the path of this one. If you want to visualize this data underscore OR, not all, I want to visualize only top five data points. Then you can run data underscore OR dot head, and these are the top points. Okay.
How does
And
it know how many, the number you have not given there?
And number of samples, madam.
Yeah, but head when you say.
By default, it will consider 5. If you mention anything like 3, then it will be 3 only.
Yeah, okay.
By default,
So
it will take 5.
default is half the samples, is it?
Not half the sample, by default 5.
Okay.
Default 5, whether it is a lakhs of data, by default dot
Okay.
head function will throw the top 5 samples from the data.
Okay.
So this is the data. So we imported data. So what next? We import the data. What next? So this is the data. You can observe the data. So it's okay. It is because all the values are between 0, 1 only. No need to normalize in this scenario. So directly I can go to split the data. So instead of using data underscore OR, actually initially I thought to normalize the data, but it's not required here. Okay. So this is the data. Now, how we split the data? We have to split the data for the training purpose and also for the testing purpose. So how we split the data? Anyone? Okay. So we have a library to split. We can do it also. We have a library from. Any doubt, please?
No, sir.
Okay, thank you. sklearn. From sklearn dot model selection. Import. What we are going to import to split the data? Yesterday we discussed day before yesterday, I think so. What library is required, or what method we require to split the data? The method is train
test split.
train underscore test underscore split, that method. Now you can pass that one. So what it will give the values? It will give the X train, that means input data, right? Also it will give the input data for the testing, and also it will give the Y train, and also it will give the Y test. Right? X train, X test, Y train, Y test. And you have to call this function, okay? Then what we have to pass? We have to pass this input and this output. We have to pass the input and output. So how we pass the input? Data dot X, right? Because our input is X label. So data dot X and data dot Y output. Next, we have to pass test underscore size. So let us do 10%, that means 0.1, right? And we have to initialize random state. Sorry. Random state equal to some value. Sorry. Random. So random state, some value you have to give. Any value you can give. So then what happened? The data will be split for the train and testing purpose. If the X train means input data from the training data set. X test means input data from the test data set. Y train means output for the training data. Y test means output for the test data. And this is the method I am using. I am passing the original input and the original data output, total data set, complete data set input, complete output values from the data set. And I have to pass the test size, how much percent of samples you want to use for the testing, and you have to use the random state. So simply run this code. That's it. It will split the data. So if you want to visualize, so what is the X train like that? So we can use fp print X train, close this one. Then you got the whatever the training samples are there, input samples are available here. Similarly, if you want to see the corresponding output, then you can use the Y train. Print Y train means, so these are the corresponding outputs, all are available. Okay. Now splitting of the data is completed. Now tell me what to do. Now tell me what to do. So we initialize all we imported the required libraries. We read the data also, and we split the data. Now what next?
Now the model creation GM we will.
Right, madam. Now we have to start the writing the algorithm to update our model parameters of simple linear regression model based on the momentum optimizer, based on the available data, training data. Okay, training data only used to train the model. Testing data only for the testing purpose. So if you want to see what is our test data, that's also it's better to keep aside. Y test and print X test. So this is the Y test is the output is 0.78 and X test is a 0.9. Okay, we will keep it aside. So now we have to write the program or algorithm. So outer loop is for, and before that one, actually training perspective, how many nested loops we have? Actually 2 nested for loops. Outer for loops, it will repeated until number of epochs reached. Number of epochs equal to 1000. Okay, number of epochs is 1000. And whatever the inner loop, inner loop that means sample loop will be repeated based on the number of samples available in where? In X train or
Train
in X
data,
test?
X train, yeah.
Train, that's it. So we have to initialize that also, it's better. So n equal to, so X underscore train, dot shape 0. 0 means number of rows in the X train data. And if you want, you can print that n value, nothing but number of samples. So number of samples are 8. Number of samples are 8 here. Number of samples. Okay. Now start the coding for outer loop, iter in range, of epochs, iter in range of epochs, right? Semicolon, colon, for sample in range of what I have to pass here,
In here.
n number of
N.
samples.
Yeah.
So what next step here? Inside the loop, inside the for loop. So first calculate the GM. That's it, right? So you can see this algorithm inside the for loop. These are 3 steps only: gradient calculation, velocity or step length, and update. That's it. Whatever the algorithm you can take, these are the 3 steps will be repeated. The 3 steps will be repeated. So what we can write here? So GM calculation, GM equal to -1, that is the minus into. Now tell me what I have to write. What I write here? You can see
Y
this one.
train.
Yes, ma'am.
Yeah.
Y train. So Y value, actual value will be available in Y train. So Y train dot, I want to log that variable, log which value I have take, sample, sample.
Hmm.
Okay. I want to print this one, what it will come. So print, maybe a pass the 0. Yeah, okay. This is the, okay. Just I'm checking whether the parameter is reflecting or not here. Okay, so that Y value coming here. For that sample, whatever sample equal to 1, first sample equal to second sample, like that. Minus M multiplied by, anyone tell me? So actual value is M into X. X coming from? X is coming from?
X train
X
only.
train. X train dot ilog, and we have to pass that sample. That X only we have to consider. If sample equal to 1, first sample output, first sample input we have to pass. So Y minus MX minus C multiplied by same X again we have to pass. So this is how we can calculate the our GM value, and how we can calculate the GC. So GC equal to, at end you have to remove this part. No X in case of GC calculation. Okay. So once we got these two, what next step? We have to, next step, after calculating the gradients, we are going to the velocity updation. How we update the velocity values? Vm equal to gamma multiplied by Vm minus eta multiplied by gradient, Gm, right? Similarly, Vc equal to gamma multiplied by Vc minus eta multiplied by Gc. So this is the gradient calculation, and this is the velocity updation. So after that, what we have to do? Update the model
New value
parameters.
of M. Yeah.
M equal to M plus Vm, and C equal to C plus Vc. That's it. Actually, this is what happened for any machine learning model. I'm taking the very simple things because we are able to understand easily. And if you go for the complex models, we are just visualize. See, suppose if you want to understand what happened behind for a complex model, we can't visualize and we can't show like this. It is a very, very big code also. But same process will be happen. Only thing is number of parameters increases and number of these equations are increases. Suppose if your model contains the 10 model parameters, let us zoom. Your model contains the 10 model parameters, then what we have? Here, why it's the 2 gradient calculations? Anyone tell me why it's the 2 gradient calculations? Why it is the only 2 velocity calculations? Why it's only 2 updates? Because we are working on the simple linear regression model, which has only 2 model parameters. So only 2 model parameters, so 2 gradients, 2 velocities, 2 updates. But if it is a 10, same thing, right? 10 gradient calculations, 10 velocity calculations, 10 model updations. If it is a 1000 parameter model, then 1000 gradient calculations, 1000 velocity calculations, 1000 updations. That's the only change. The number of equations will be increases, the complexity of the program is increases, the computation time is increases, but logic is same. Okay, so that's how we can. So that's, I think it's completed, right? That's it. So these 3 steps should be writing here a step-by-step process that is happening in. That's it. The training process will be completed. So if suppose someone is using the libraries like what's yesterday some Sarek said that linear regression or dot fit. So whatever the dot fit in the back end, the code not exactly similar code will be run in the back end side dot fit. If you're using the dot fit method in the back end of the dot fit method, for the dot fit method we have to pass the white train and X train. Suppose what I'm saying, are able to understand the persons who are working on the libraries earlier. Suppose if you want to develop the simple linear regression model from the sklearn libraries. So you can use the libraries directly and take an object, and after creating an object, you have to write object dot fit, and you have to pass 2 parameters. One is the X train, another is the Y train. So in that fit function or fit method, similar code will be there that will carry and X train, and it will do this process and finally gives the final M and C values. Right? But I am opening that one. It's like a black box. Yes, I am trying to open. I'm not saying that same code exists, but similar code may exist. Next. So let's assume the training was completed. So when completed, what I have to do, I want to print. I want to that M and C values, M equal to 0.2, sorry, M equal to, so percentage 0.2 F and C equal to percentage 0.2 F, and we have to pass M comma C. That's it. Now run this algorithm. I'm giving 1000 epochs, so it will be run for 1000 epochs. Now run this one. It will give the M and C values. My M and C values are around 0.2 and 0.59. These are the M and C values. Now anyone can tell me what is the next step. So now model parameters are calculated, updated for the 1000 epochs. That means the training of a machine learning model, simple regression model is completed. The model parameters are updated. So once the model parameters updated for a given number of iterations, what we are going to do next? Anyone? Or the next step? Training completed. The training was completed, then what we have to do?
So testing now we have to check with
Right, madam. We have to
test data.
find the
data.
error matrix.
Yeah.
We need to find the error matrix. So error matrix means we need to calculate the testing errors and the training errors. So to calculate the testing errors and training errors, so first actually this X train and Y train, what I'm showing here, the X train and Y train values, all are the data frames. Now I want to convert it to the array format. So to convert into the array format, so you need to use this part. So every X train, Y train, X test, Y test, I'm converting to the NumPy array. Converting into the NumPy, just X train equal to NP dot array. I'm trying to convert into the array format, NumPy array format, and pass this data from X train. The similarly Y train, and similarly X test, and similarly Y test. Just only format changes. I'm changing the format only. Once it is completed, now what we have to do? We need to calculate the training errors, right? So calculate the training errors is nothing but how we calculate the error. Error is nothing but the difference between the actual output and the predicted output on the training data. How we calculate the error? Error is calculated based on the difference between the actual output and predicted output on the training data, right? Okay, so we have the actual output of the training data where it is available, Y train. Okay, Y train. And where we can get the predicted output, so we need to calculate the predicted output based on this M and C values. Based on this M and C values, we need to calculate, right? So for that one, so just I want the same code I am using again and again because no change here, right? So only data M and C values are changes and your data will changes. So what I am doing here, just initially I am creating a empty array, empty matrix. Every sample, every input from the X train I am taking and multiply with M, add to the C, whatever the prediction is coming, that will be appended to this empty matrix. That's it. Okay. Now I'm getting the predicted outputs on the training data. Now I want to do the same thing for the test data as well. So I want to create one more array, test array, ypred test array as an empty array. And I have to take every input sample input value from the test data, x test, and pass that input x and multiply with m, add the c, and whatever the variable, store it as a y underscore p underscore ts. And this should be append to your this matrix. For this empty matrix, you have to pass. At last, you have to convert this empty matrix as a NumPy array, because I want to compare this predicted output with the actual output ytrain, which is already converted into the NumPy array format. Ytrain already converted into the NumPy array format. So now what are the calculating here? I want to try to convert into the NumPy array format. Then I can compare both arrays. I can easily calculate the error easily. So I calculated the both predictions on the training data and the predictions on the test data. So after that, what we have to do? We need to calculate the errors. Sorry, we need to calculate the error. So anyone tell me how we can calculate the error? We have the libraries in the sklearn. That is the from sklearn dot metrics, import. What we are going to import? First import mean absolute error. Similarly, from sklearn metrics dot metrics, so you can import mean square error. So now, if you want to calculate the mean square error, MSE, mean square error, equal to, you have to take this object, mean square error, and what we have to pass inside? I want to calculate the mean square of my model on the training. Let us assume this is for the training. I want to calculate the errors for a training data. For a training data, I want to calculate the errors, training errors. So now tell me what I have to pass inside to calculate the mean square error. Just I am importing the mean square error.
Why
object,
training data difference?
Right, man.
Yeah,
We have to
between-
pass the actual output and predicted output we have to pass. Because based on that only we are calculating the mean square error. So mean square error equal to 1 by n sigma I equal to 1 to n y actual value minus y predicted value whole square. So we have to pass the actual output value and predicted output value here. So how we where the actual output values are available? Where the actual output
train.
values are available? Ytrain. So y underscore train actual values are available. And where the predicted values are available? Y underscore
Why predicted?
predict something I have written earlier. Yeah. Y predict train.
Train.
Yeah, this one.
Mm.
So these two will give the mean square error. Similarly, if I want to calculate the mean absolute error, so we have to pass this one. Take this method, and what we have to pass again? We have to pass the actual output and the predicted output with the training data. Done. Okay. Now, if you want to calculate the root mean square error, what we have to do? The name itself says that root mean square error. Already we have square error. Simply take it a root. So root means I think mt dot sqrt. Yeah, of MSE. Mean square error. That is called as the root mean square error. So once you got the all these things, mean square error, mean absolute error, RMSE, simply print. So if you want to visualize, so what are the values? So MSE equal to something like MSE equal to percentage 0.2 F comma 0.2 F comma MSE, and similarly print if you want to MAE, mean absolute error is equal to percentage 0.2 F comma MAE. Okay. And print what next? So RMSE equal to percentage 0.2 F for comma RMSE. That's it. So all the training parameters will be training errors will be printed here. So I think I didn't execute the previous one. So execute this one to calculate the predicted output on the test data. Now run this cell to calculate the errors. It's showing some. Okay. That is the thing when we are working parallel on the same what's called different programs. The syntax will be different. The percentage can be used for the comment in the MATLAB, but here we have to use this one.
Yes.
So now you can see the errors in the training data. All are almost 10 to the power minus 32, 0, 10 to the power minus 16, 10 to the power minus 16. Almost I'm getting the very good errors in case of the training. And we have to do it for the testing also. So we have to do it for the testing also. So testing means you have to copy same thing. You no need to import again. Already imported, so no need to import again. Only remaining part will you can copy. But what the change? Now I want to calculate the testing errors. I want to calculate the test errors. I want to calculate the test error. So how we can calculate the test error? Simply pass y test and pass y pred test. Right. Okay. And here also we have to pass both y test and y pred test. Okay. That's it. Now you can run this one. Then you are able to see your testing errors. Your testing errors also almost 0. Your testing errors also almost 0. Okay, 10 to the minus 32, 10 to the minus 16, 10 to the minus 16, almost 0. Let us assume you are happy with both training and testing performance. Then what you have to do? Simply deploy your model. So deploy your model means in the back end of application, you have to move your model parameters. So what are the model parameter values we are getting here after training? 0.2 and 0.6. So M equal to 0.2 and C equal to 0.6. Okay. So what next? We have to give a permission to you once the application running. So you have to give the permission to the user. You have to give the permission to the user to enter the input value. So that's why X equal to input. X equal to input. So you have to give some instruction like enter X value, enter X value. Okay. Once the X value is entered, then what you have to do? Now, you have to pass the architecture. Based on the architecture, the application will do in the back end of your application, some process, some mathematical operation will be done based on the architecture of your machine learning model that you develop. Then the output will be printed on the top front end. So now that's a y X value. Now y equal to, then y equal to M multiplied by X plus C. And finally, you can print. You can print as predicted output y equal to percentage 0.2 F comma y. Okay, that's it, right? So if I run this code, will it give a right answer for me? This is the application code, backend application code. Okay. So if I run this cell, it may throw an error, right? It may throw errors. Let us, okay, I want to verify. So I want to verify some X value I will give. I want to check whether I'm getting the output right, correct output or not. Okay. I want to pass 0.5. I'm expecting 0.7. So just pass 0.5. I'm expecting a 0.7, but it throws an error. Why? Anyone? Why it's throwing an error? Here the error shows. What happened? Anyone, please? Okay. So the thing is, what are the input entered by the user that will be considered as a string by the variable X. We have to do the typecasting. That means we have to convert into a float. We did already. Last 2 days we are doing the same thing. We have to convert into the float. Now you can run. And it is asking, you have to enter the input X value and the output is 0.7. That's what we are expecting, 0.7. That's how your application will predict for a given input what will be the output that will be predicts. I'm not giving anything. What I'm getting from the machine learning model, I'm deploying here. Now my model is predicting what is the value of output. So this is about the writing a code for training process of a simple linear regression model using the momentum optimizer. That the only change when algorithm to algorithm, the only change you are able to see here in this loop. That's the only change you are able to see. That's the training algorithm. And before this one and after this one, all are same. You can use the same piece of code and again. Only thing is how you are able to, even though I'm giving some exercise for you, even though I'm giving some exercise, some assignment for you, you have to spend some time. Only you feel difficulty while writing this step. And remaining all are no change. You can use these steps and you can use all these steps. Only main concentration is required in this cell while writing the algorithm. Okay, fine. So now it is at 3:16. I will take a break for the 15 minutes. And post break, as I mentioned in the brochure, so I want to train a simple linear regression model for a real-time application. That means I want to predict the load on a substation.
Programming is రాసినట్టు group లో పెడతారు.
Okay. So
Sir, excuse me.
sir,
I have missed the class yesterday actually. Yesterday's
Sir.
session I have missed it due to some my personal issue.
Machine learning first నుంచి పెడితే బాగుంటుంది.
Can I get this previous recording session, sir?
Yes, sir. Already that is the link is posted in our wall. I think I posted yesterday. No.
The recording.
And so this is my load data. So Y is nothing but the a particular hour of the data, that is the 4,931 kilowatts, and 24 hours back data is 5,551. At a particular time 4,775, and 24 hours before that is the 4,983. Like that, the data is collected and processed in order to predict this Y. That means load at a particular time based on the load available 24 hours before. So this is my input, that is called X is nothing but the load 24 hours before, Y is nothing but the load at what time you are going to predict. So this is the 4931 and it is the 5551. So I want to predict this one based on this value. Because it is a simple linear regression model, I am taking the one input and one output. And the model complexity increases, the number of input features increases, number of model parameters increases, number of gradient calculation equation increases, number of velocity calculation increases, number of updations increases. The complexity of the model, complexity of the program also increases with respect to the complexity of the model. Okay. Now I want to write the code in Jupyter Notebook. I want to open a new notebook. So after completing this exercise, I will move to the adaptive learning rate based optimizers. Adaptive learning rate based optimizers. Okay. So here what we are going to work. So momentum optimizer based simple linear regression model, that means trained with simple linear regression model trained with momentum and on the load prediction, load forecast or load prediction. So this is the what I am working. Okay. Now I think first tell me we need the data, right? So try to import the data first here. Try to import the data into the Google Colab. So click here and load data sample regression, simple regression. Done. Now tell me what is my first step. Same steps I said, right? So before that learning process, after that learning process, all the steps are almost same pipeline. Okay. Now tell me what the steps we have to follow. We have to import libraries. So import NumPy as NP, import pandas as PD, import random, to random initialize the model parameters, import math library as empty. So just importing all the libraries. Now tell me what is the next step. Please, anyone, please tell me what is the next step after importing the libraries. What is the next step? So whatever the problem statement, the sequence will be same. Only the data will be changes. That is the main crucial. Once you start working on a particular model, the same steps can be used for any problem. Only data changes. So you have to more focus on the data. Okay. So what is the next step? Anyone, please? What is the next step? We discussed it, right? Already.
Yeah. Here also
So-
initialization.
In initialization. So M equal to, we have random initialize the model parameters because we are using a simple integration model. So random initialize the simple integration model parameters M and C. So M equal to random dot uniform, the range of -1, 1, and also C equal to random dot uniform and in the range of -1, 1, M and C. And also we have to initialize the eta value as 0.1 and also initialize the gamma value as 0.25 and initialize the number of epochs as 1000 and anything else. Initialize the velocity Vm equal to 0, initialize the velocity Vc equal to 0 and anything else we need to initialize? I think all are covered, right? MC, eta, epochs, data okay, n okay, gamma 0.5 okay, all are initialized, right? So simply run this cell. That means initialization is completed. So what next? So this is the real pipeline I'm telling one by one. So what next step? This is the complete pipeline to write a code for any machine learning work, machine learning based works. But slightly the coding part will be changed based on our problem, based on our data. Slightly changes. The logic will be same. The flow will be same. Import the libraries, import, initialize your values, like that. Anyone, please, next. And I'm not discussing about the what's called data pre-processing techniques here. I'm mainly focus is on how optimization algorithm helps to update the model parameters of your simple linear regression model during the training process. If you're able to understand that part, and the same thing will be repeated for the multiple, same thing will be repeated for the polynomial, same thing will be repeated for the ANN, like that. Be mostly based on supervised learning algorithms. Okay. So next, please. So initialization is completed. What next? So what will be the next step? Initialization completed, importing the libraries completed. What next? What is the next step?
Data.
So next step, data. Data, first we have to read the data. So data, original data, that's equal to pd dot read dot what I have to use, sorry, pd dot read underscore what I have to pass. Tell me, this one or this one? I have the read underscore Excel, I have the read underscore CSV. Which one we have to use? So we have to use read underscore CSV because my file is a CSV format, .csv format. So open the bracket. Within the bracket, we have to pass copy path and you have to pass the complete line. Then data, if you want to see that data, few samples of your data, then you can use that variable name and dot head, then it will give the top 5 samples of your data. So this is the X and this is the Y, top 5 samples. See, so when the load is 5,551, next 24 hours later, the load will become 4,931. So like that. So now data is completed. Next, what next step? It's the real-time process I'm explaining. Just I'm importing the data. Next, what next we are going to do? See the values properly, then tell me what we have to do. What will be the next step? Just give me some time, please. Sir. Sorry. Now tell me what is the next step, anyone, please. If you have a problem to speak out, you can use the chat box also. You can chat using the chat box. Otherwise, you can unmute and you can tell. So data reading is completed. Next, what is the next step? Anyone? What will be the next step?
I have to split the data because it's a very
No,
huge data.
that is the next step, madam. Before that, we have to do one thing. In the real-time works, we have to do one more thing. So see this data samples properly and what we have to do. We discussed it already. Yesterday also we
Normalizing.
discussed. Yes, madam. Yes, that's it. So normalization. I have to normalize the data, and normalize the data I want to store in a variable called data. So data equal to how we do the normalization: actual value minus minimum value divided by maximum value minus minimum value. Yesterday we discussed it, right? So actual value means data underscore OR, original data, minus minimum value, right? Data underscore OR dot min, dot min. Okay, divided by, and in the denominator, what we have? Data underscore OR, that's the original data, actual data, and I want the maximum. So dot max minus data underscore OR dot min, right? The actual value minus minimum value divided by maximum value minus minimum value. So if you want to visualize the data, you can use data dot head. So data contains the what's called normalized data. Okay. So if you want to see, you can click here, you can see the values. See, this is called normalized. Actually, these are the values in terms of the kilowatts, and these are the values after normalization. So after normalization, what may be the next step? So importing the data, see first, importing the libraries, initialization, importing the data, normalizing the data, what next? After normalization,
Now
what
the
we have
actual
to...
algorithm.
No,
Yeah.
madam. Before actual algorithm, we have to do one thing. After normalization, not directly go to the algorithm. In between, we have to do one thing. For the previous question, you gave that answer to me. Previous question, you gave that answer, madam. There is a splitting of data is required. We will not split the data as of now. Just to normalize the data. We have to split the data for the training and testing purpose. So to split the data, we have to import the required libraries from sklearn dot model selection import. So what library or method we are going to import? That is called train underscore test underscore split. And what are the things we are getting from this method? One is called xtrain. You can use any variable. For easy of understanding, I'm using the xtrain. And we got the input test data. We got the output train data. And also we got output test data equal to what's called train underscore test underscore split. Pass. What I have to pass? My inputs and outputs, actual inputs and outputs. My inputs are X and Y, but a variable is data. So what I have to pass here? Data dot X, comma, data dot Y, comma. We have to give test size. So I'm 10% of, the data is somewhat large, so that you can give the test size more also, not an issue. So I want to use 70% of data for the training purpose and 30% of data for the testing purpose. Okay. So I want to use the 30% of data. 30% means 0.3 of data for the testing, and remaining 70% will go to the training purpose. And we are using the random state equal to some parameter you can use like this one. Okay. That's it. Just running the code. Now the data splitting of the data is happening. So xtrain containing the training input data, test containing the testing input data, y train output for the training, and y test output for the testing. Okay. So what next? Now, as madam told, now we have to write the code for the algorithm. So same. So algorithm outer for loop for, and before that one, we have to identify the number of samples in the data, right? In the data means which data? Training data, right? Not testing data, not whole data, because the training data only used to train the model. Training data only used to update the model parameters. Sure. Definitely, some Bon Prakash asked me to share the data. Definitely, actually, the data is available in cloud, open source only. Just I published the data. So if anyone want, they can use the data also. So, and one more suggestion from my side, whenever you are working on any machine learning related projects, whenever you are developing some new data, so in order to make it useful for the other faculty, other researchers, other fellows who are working on the machine learning related projects, try to publish the data in a repository, public repository. Then anyone can access from them. Okay, they can once they use the data from that repository, so definitely they will cite. They will definitely they have to actually cite that repository path. So I will 1 minute. Okay. So there is a called actually I'm logging into my page, but actually it's not required for others. I will share one link. From that link, you can download the data. So this is the data that is available. So from here, you can download the data. So this is my DOI of the data set and everything is available. This is how to cite that data set. So just posted in our WhatsApp group. Done. Okay, I hope it's clear now. Fine. Okay, just already posted the data. So as madam said, after the splitting, okay, before splitting, going to writing a code to train our machine learning model. So what we are going to do? We have to extract the number of samples. So number of samples equal to x underscore train dot shape. So first column, that means number of rows. So number of rows in a data set is nothing but the number of samples. Okay. So if you want to see the value, you can write print n. So you can write something like number of samples in training data equal to %d and a comma n. So number of samples are 1512. That means 1500 samples are available in the training data in order to train the model. Okay. Now, after getting the number of samples, now we have to write the code for the algorithm to update the model parameters using the momentum optimizer. Okay. So what are the steps here? We already same process. So for iter outer loop, iter in range of epochs. Okay. For sample in range of n number of samples. So now tell me what to do. What we have to do. We need to calculate the gradient GM equal to. So calculate the gradient calculation. So that the -1 multiplied by actual output. Actual output value is available where y underscore train, right? Actual outputs. Actual outputs y underscore train dot log for that sample. For that sample, sample equal to 1, first sample equal to second sample. For that sample, y value, actual value you have to take, minus m into x. X is coming from train data, x train dot ilog, okay, and pass the sample mx minus c and multiplied by, you have to pass this x again. Okay, next. And whereas GC equal to, you can copy the same line again, no need to type, I don't want to type again. So GC equal to, you can remove this part. Last x no need. So only minus y minus mx minus c only, right? GC. So after calculating the GM and GC, what we are going to do? Velocity calculation, right? So VM equal to, VM equal to gamma into VM. What next? Minus, I think you are able to recollect. So what is that expression? VM equal to gamma into VM minus eta into GM. VC equal to gamma into VC minus eta into GC. So VM equal to gamma into VM minus eta multiplied by GM. And VC equal to gamma multiplied by VC minus eta multiplied by GC. That's how we are updating the, how we are calculating the velocities. After that, we are going to update our model parameters m equal to m, what's called m plus VM, and c equal to c plus VC. That's how we are updating the model parameter. That's it. This is only the our code to train the machine learning simple integration model, or to update the model parameters of a simple integration model using the momentum optimizer. Only this part changes, you can see these two lines. So this is the training process. So if you run this one, the training process will be initiated. It will run for the 1000 epochs, because I'm giving the epochs equal to 1000. It take more time because the data is large, not like a previous case. So in the previous case, we have only very small number of samples. I think 9 or 8 samples only. But here in the training, we have the 1512 samples. And I'm running the algorithm for the 1000 epochs. That means every model parameter will be updated 1512 into 1000 and 2 model parameters into 2. So you can calculate how many times the model time will be working. Done. So that's over. Okay. So now suppose if you want to print the updated model parameters, print m equal to percentage 0.2f, comma, c equal to percentage 0.2f, comma, m, comma, c. Okay. So these are the m and c values. 0.8. So finally I'm getting the m and c values as 0.8 and 0.07. So after m and calculating m and c, what the next step for us? For the next step for us, we need to calculate the errors, right? So we need to calculate the errors. So to calculate the errors, what I'm trying to do is, we have already code, right? So if you want to calculate the errors, first of all, you have to calculate the predicted load for both training input data and also for the testing input data, right? So you have to calculate the predicted load for the both training input data and for the testing input data. Okay, now. So that's it. So y underscore pred train a null empty matrix, and from the every training data input I'm taking and multiplied with m, added the c, and the rest value is assigned to a variable. That variable is added to this empty matrix, and finally this empty matrix is converted as a numpy array. Okay. So before that, okay. First I will calculate all the predictions. For the training data is completed. So after training data completed, what we are going to do? We are going to do for the testing data also. We are going to do for the testing data also. So for the testing data, you have to create a empty matrix initially and take every input from the test data and pass that input to the model. It will multiply M and add C. And whatever the predicted value is coming, you can store it in a variable called y underscore p underscore ts. That's your choice. Once that was stored, that value should be append to this matrix. What is the value you are getting predicted, that value should be append to this empty array. That's it. Now you have to convert this predicted output, the array, the matrix which containing the predicted outputs on testing data will be converted in the array format, NumPy array format. Good. So now we have the predictions from the training data, predictions from the testing data. So next we are going to calculate the errors. So for the errors, we are going to pass both weight, and that means actual value and out predicted value, right? So predicted values are already in the NumPy array format. Now you have to convert the actual values also in the NumPy array format. You have to convert the actual values also in the NumPy array format. What is the actual value? Y underscore train is equal to np dot array pass y underscore train. That means I am converting the y train into the as an NumPy array. Similarly, y underscore test also we have to convert as a NumPy array. Y underscore test. Okay, that's it. We are coming. So after that, what we have to do? Find the error matrix. So first we will work with training data error matrix. So if you want to calculate the errors, what we have to do? First we have to import the libraries. We have to import the libraries, right? So from sklearn dot matrix import mean square error. Similarly, from sklearn dot matrix import mean absolute. Here I write a spelling mistake. sklearn from sklearn dot matrix mean absolute, right? Absolute error. Now, if you want to calculate the MSE, what you have to do for this mean square error, pass your y train value, and also you have to pass y underscore prediction train, right? Training data I want, right? That's it. Okay. And if you want to calculate the mean absolute error, and take this one and paste here, and you have to pass the again actual value and the predicted value inside. And if you want to calculate the RMSE value, simply you can write empty dot sqrt square root of mean square error. It is a root mean square error, right? That's it. If you run this piece of code, of course, wait, showing some. No, it will work. I will see. Or two values, and Viprate train also different values. So why? Okay. Anyone please identify what problem here? Anyone? I did some mistake here. Anyone able to identify what happening? Anyone is there inside?
Evaluating train to test. Predicted
Right.
train.
Here you can see,
Yeah.
madam,
Yeah.
test data, right? Actually, I am
Yeah.
using the same variable in the both cases. That's why it's getting different different problems. Here it should be y pred underscore test. Here it is y prediction underscore train. Previously, I kept both are train. That's the issue actually.
Mhm.
Test values I have to feed. Now you can see prediction train. Done. Okay. Now I think it will work now. Oh, done. So you want to print the values, right? So print, if you want, you can print. So MSE equal to percentage 0.2F, comma, MAE equal to percentage 0.2F, comma, RMSE equal to percentage 0.2F. I want to print all. So MSE, MAE, RMSE. So you can see the output values. That means error values. You can see error values are 0.0173, 0.096, 0.13. Similarly, we can do for the testing also. Similarly, we can do for the testing also. Similarly, we can do it for the testing also. Okay. So for the testing, what we have to do, instead of training data, we have to pass the test data. Test, and we have to pass the test predictions. We have to pass the test predictions, and we have to pass the actual test values, and we have to calculate the all the things same as. So these are the testing parameters, testing value. That means errors in the testing. So let's assume we are happy with the training and testing. Then what we have to do? We have to deploy the model. We have to deploy the model. Okay. So now we are going to write the code here for the deploying purpose. We are going to write the code for the deploying purpose. But we already discussed, if you want to deploy the model, so we have to calculate the, somewhere I have developed the application earlier. 1 minute. Now I want to deploy the model. What we are doing here, you can see, we are calculating something. Why we are calculating these parameters? Anyone tell me? In a previous yesterday, bicarbonates deployment application, if I want to deploy an application to predict the bicarbonates in a well water based on the pH value, I am calculating these values and pasted there. So what is the need of this one? What is the need of this one? Anyone please tell me?
For normalization and
Yes, madam. So in the when we are going for the deployment case, user enter the load actual value, but our model is trained on the normalized data. So once the user enter the actual load data, original load data, 24 hours back, then that load data should be normalized, and normalized data should be passing to the machine learning model, and model will predict normalized output, and normalized output reverse back calculate the actual value. So for that, we are using these things. We have to calculate the what is the maximum value, what is the minimum value in input, and what is the minimum value, what is the maximum value in the output that we are going to calculate. Okay. It's not deployment, but we have to calculate before writing the code for the deployment. Okay. So I am using the same data underscore OR variable only. So I can use as it is, not issue. We are using the data underscore OR variable only in case of the load data import. So just I am using this one, but only thing is, so this is the input, right? 0 means input X, 1 means output Y. So input is nothing but the L24. That means 24 hours back load data minimum value. This is the 24 hours back load data maximum value. So this is the LT minimum value, and it is the LT maximum value. You can use any variable here. Just for a easy of understanding, I am keeping like this. If I want to predict the load at a particular temperature, you have to feed the 24 hours back load data. That's why I'm giving this syntax notations like that. You can use anything. So you can use, now you got the minimum value, maximum value for the inputs and minimum value, maximum value for the outputs. Now tell me, you have to, what are the values we are getting? We have to print it now. Print L24 underscore minimum, comma L24 underscore maximum, comma LT underscore minimum, comma LT underscore maximum. Okay, so it will print the minimum value and maximum value for every input and output. Now those values you have to feed it now. So what is the value of L24 minimum? What is the value of L24 minimum? That is available here, 3,378 after round it off. And L24 maximum value is equal to L24 maximum value. What is the L24 maximum value? This part, 8,842 kilowatts. And what about the LT minimum value? LT minimum value is equal to how much? LT minimum value 3,000. So same. So same values are there. You can see here also same values here. So 3378 and LT maximum equal to 8842. Okay. Now, after that, what we have to do? Now we have to give a permission. So later we have to deploy the model. Deploy the model means you have to load your model parameter values, updated model parameter values. What are the updated model parameter values? Updated model parameter values. You can see 0.8 and 0.07. You can see 0.8 and it is a 0.07. So you have to pass those values. 0.3, 0.3. Semi-equal to, sorry, 0.8 and 0.07. So it is a 0.8 and C equal to 0.07. So once the model parameters are deployed in the application, next what we have to do? Now your application will ask the user to enter the 24 hours before load data. Let's assume I want to predict the load at 5 p.m. today. Now it will ask what is the 24 hours load data? What is the yesterday's 5 o'clock load data? That must be coming as a pop-up, right? So L24 hours back data equal to input. So it will ask enter 24 hours back load data. It will ask like that. Okay. Now once you got this data, what we have to do? So don't feed this data as it is to your model architecture. We are going to normalize the data. So L24 norm equal to, how we normalize the data? Actual value. The actual value means you have to convert it to typecasting because it's treated as a string. It will be considered as a string. You have to convert into typecasting. Float, pass the L24 minus what you have to feed here is the input data, right? So you have to take the input 24, L24. So you have to take the L24 minimum divided by, that means X minus X minimum divided by X max minus X minimum. So this is called your maximum value. L24 maximum value. Okay. This is how normalization will do. Once the normalization is completed, then what we have to do? We have to calculate the predicted output. So LT, predicted output equal to M multiplied by your normalized input, norm, because your model is trained on the normalized data. So M into X plus you have to add the C. That's it. So let what happened? So now your model will give the normalized output. This is your normalized output. Okay, I will write it as a underscore norm. It is the normalized output. Now I want the actual output. How we can get the actual output? So actual load equal to how I got? Yesterday I told. How I got the actual outputs? Yesterday I told.
Normalized output multiplied
Yes,
by
yes,
maximum
madam.
number
Right,
of
madam.
nodes.
So
Yeah.
normalized output into, so is the normalized output, Control C, Control V, multiplied by max minus minimum. So LT max minus LT minimum
Plus
less LT minimum. So this is the normal. Once you got this one, so you can print the pop-up. That means you have to give the output on the application. On front panel of your application, you can print what you want. Predicted load is equal to percentage 0.2 F, some kilowatts, comma, so LT. So this is how we can write the code in the backend of your application. So you can run this one. It is asking what is the load. Let's assume I am entering the 24 hours back load equal to 2000 kilowatts on the substation, my substation. Now it's asking, saying that, so next 5 o'clock, it will give, it maybe the load is around the 2658 kilowatts, 2568 kilowatts, like that it will be printed. Okay, so this is how we can work on the applications. Okay, so hope it is you are clear with all the things. Means import the data, initialize the values, read the data, normalize the data, feed the data, train the model, and calculate the predictions on the training data, testing data, and calculate the training error and testing error. Let's assume you are happy with the training and testing error, then write the code for your application development. Once the application was developed, so that application only will run. The backend, the models will be uploaded. In the backend, your machine learning model runs, means your model parameter will take care of it. Your model parameters and your what's called your architecture. So it's asking something like 3000, maybe let's assume, then it will give the 3458 like this. Okay, so these are how the complete pipeline for the, see, these are the very, the main intention in this training program is to make you understand the process of training of a model and a small simple pipeline, not to build an effective machine learning model. This simple language model is very, very basic model. Don't expect it will create a wonders for your real-time problems. No, very, very simple problems only it will work like this. Okay, so this is all about the how we can work on the real-time problems using the momentum optimizer to train the simple linear regression model, to update the simple linear regression model. So is it clear? You have any questions? Okay. So and one thing, Madam Kalpana, Madam, are you are you listening?
Yeah, yeah.
Yeah. So yesterday, you asked one question, that is, sir, you don't need to reverse normalize the data before calculating the errors. Okay, madam. So here I am calculating the errors on the normalized data, but practically speaking, this is not a good option. Why? Because all the data, while calculating the errors, all the data are in terms of the normalized data only. Normalized data means all the values are between the 0 to 1 only. So when you are comparing, definitely the errors is not much. It may be a very small value.
Yeah.
Right, madam? So if we see the small
Yes.
value, we can't cheat our client. So we are getting very small 0.02 like that. No. So actually, here I'm for academic purpose, I'm showing like this, but you are working for a real-time project. I am suggesting, so before calculating the errors, it's better to get the original data, original predictions. So you have to do the get original predictions and give the original output and original predictions, actual predictions in terms of the kilowatts, not between the 0 to 1, actual values in terms of thousands. Then only you are able to predict, figure out correct values. Maybe here it is showing as 0.017, 0.096 like that. But once you convert into the actual values, maybe in terms of hundreds, 100 kilowatt, maybe 50 kilowatt, maybe 20 kilowatt, That's base done.
Yeah.
Okay.
So actually, yeah, for the prediction, you will use the model where normalized inputs are only used.
Here,
But
madam.
for the final calculation, we will get the actual data and compare.
Right, right.
Yeah.
So why actually, if you observe this line, we are asking the user to enter the data.
Yeah.
User enter the actual data only. He don't know what happened in the back end of the program, normalization.
Yeah.
He will see the reading, or he will open his register, day-to-day register, and he shows yesterday 5 o'clock load is 3000 kilowatts. He will enter 3000 only. But
Yeah.
here my model is trained with the normalized data. So what I have to do now, convert this actual values in the back end of this all will do in the back end. Only user enter the actual value. That's it. So back end, it should be converted into normalization, and normalized value should be feed it, and it will give the output. That will be normalized again. So if you pop up that normalized output as a prediction value will be very, very small. He will be surprised why it is showing a very small value. I know my load is like in terms of thousands. That is what happened because I am printing the direct normalized output. So that's not a good choice. Then what you have to do? You have to reverse that one, and then you have to find the you have to print the actual value. Then it will go the actual values. So that's what we have to do. Clear, madam? So this is all about the momentum optimizer for the simple indication model. This case. And so this is for this one that the programming part is completed for the momentum optimizer. Later we will move to adaptive learning rate based optimizers, and we have a few more. I didn't cover the mini batch gradient descent, which is a fixed learning rate, and we have one more learning, one more algorithm, one more optimizer that is called Nastrov accelerated gradient method. These are all called fixed learning rate optimizers, and we have 1 day left. Just I will give the slight brief about for the next 10 minutes. Later we will actual. So I want to share. I want to share this notebook for the benefit of the participants.
Those assignments you have given, sir.
Madam.
We have to give it to submit to you separately in WhatsApp, or
I sent one Canvas link, madam. So if anyone interested, they can upload only that your Google Colab link is sufficient. No need to send all the information. Link is sufficient. And for that link, you have to
can
give
we
the
do
permission.
that over the weekend also, Saturday also?
Yes, madam. Yes, madam. Yes, madam. No problem.
Yeah.
No problem.
Because I may not be able to complete everything trials.
Okay.
Lot of
just
syntax.
only for the practice only. Only for the practice only.
Yeah.
I think my computer was somewhat stuck here again, like yesterday. Yeah, no, it's okay, I think. Okay. So this is my last notebook for the momentum optimizer for the load forecasting. Yeah, done. So this is completed. Now, so it's okay. Okay, fine. Now, I think it's clear with the momentum optimizer how it is updating the model parameters. Now I am trying to give some brief idea about what mean by the adaptive learning rate optimizer, what it will do, and why we are going for it. So in detail, we will discuss tomorrow, and with one adaptive learning rate based optimizer. Okay, on it. Fine. So next we are moving to the adaptive learning rate based optimizers. So adaptive learning rate based optimizers. Okay. So we are moving to the adaptive learning rate. That means adaptive learning rate means eta. So adaptive learning rate based optimizers we are going to discuss. for next 5 minutes. Just brief it, and later tomorrow we'll discuss one algorithm. Actually, we have the different adaptive learning rate optimizers like ADA, GRAD. We are going to discuss about this one tomorrow. And we have the RMS prop, and we have the ADA delta, and we have the ADA max, and we have the ADAM. So like that, multiple adaptive learning rate based optimizers are available. Still now, what we discussed about the SGD, stochastic gradient. We discussed about the BGD, batch gradient. We discussed about the mini batch gradient. We discussed about the momentum optimizer. And we have the one more thing, NAG, Nastran accelerated gradient. If you open Python Keras library at TensorFlow, you are able to see NAG. NAG means Nastran accelerated gradient. So these all methods are called as a fixed learning rate optimizers. Fixed learning rate optimizers. And these are called as the adaptive learning rate optimizers. Why these are called as the fixed learning rate optimizers, anyone can tell? Because if you observe our algorithm, we fix the eta value as 0.1 or 0.2 or 0.9 like that. We're not changing during the iterative process. We're not changing during the training process. We fix that eta. That's why it is called as the fixed learning rate optimizers. Right? So that means suppose if it is your convex function, so if it is the initial point, in this case, what happened is we are fixing the learning rate. So as we fix the learning rate, your step length also almost same. So with a constant fixed learning rate, so you are getting the outputs like this. It's a fixed learning rate. You are not changing the learning rate throughout the iterative process, throughout the updation. Okay, but whereas in case of the adaptive learning rate, but it's not a right choice, right? It's not a right choice. You agree, right? So suppose, for example, you on a bike, you started with you are in a 50 km/h speed. Okay, so if you want to maintain the same, you maintain same constant 50 km/h until you are coming near to your traffic light or home. No, right? So even though you are at a 50 km, then you are slow down, and you are going to 0 when it reaches your stop or traffic light. Okay, not you are maintaining the same, right? So similarly here also, once you are reaching towards the optimal point, when you are reaching towards the optimal point, it's better to reduce your step length, reduce your learning rate. So initially you may expect the larger learning rate, but once you reaches the optimal point, it's better to start with small step length by reducing the learning rate. So that is called as adaptive learning rate based on the iterations. So some researchers or faculty, whatever, working on the machine learning, they suggest that we have to keep the large learning rate initial point, so that you can go for the largest step lengths. Once we are moving toward the optimal solution, as iteration progresses, we are moving toward the optimal solution. So once we moving toward the optimal solution, try to reduce your step length. Otherwise, there is a problem of oscillations. So try to reduce the step length. Okay, then they give some different tactics, like maybe they write your eta hat, updated eta learning rate equal to your eta into number of epochs, that means maximum number of iterations divided by current iteration. Let's assume if the maximum some other things also there. So when the iterations are very less, that means initial iterations less means initial stage of your learning process. That means you are far away from your optimal solution. Then because this is a very small value, or you can forget about this one. This is very small value. Your n cap equal to n eta divided by eta. Eta cap equal to eta divided by eta. Let us do. When the iteration is very less, 1, 2, 3 like that, that means initial part of your training process. So initial part of your training process, you are far away from your optimal solution. So initial part, yes, the iterations value is very less. So eta value will be large. Okay, as iterations are progress, as the iteration values are increases, then what happened to this whole term? Your whole term will be reduced. Your eta hat will be reduced. That means learning rate will be reduced. When the learning rate is reduced, then your step length will be reduced slowly. So this is one of way of adaptive learning. So this is called one of the adaptive learning rate technique, but not this one. So this is something else. This is also adaptive learning rate, but it is the adaptive learning rate based on the iterations. As iteration progress, we have to adjust the learning rate small value that will be taken care by this one. But these adaptive learning rate techniques are something else, not based on the errors, these are based on the impact of the variable on the objective function. Based on the impact of the variable or sensitivity of a function on a particular variable, based on that, we will calculate the eta value, that is by using these optimizers. Okay, so I want to repeat once again. So till now, we are using the fixed learning rate optimizer, where we are keeping the eta value constant. But in case of the adaptive learning rate optimizers, we are going to adjust the eta value based on, impact of the variable on an objective function. How your objective function is sensitive to particular variable. Based on that sensitivity, you are going to update the learning rate. In this case, we are not fixing the learning rate value, but we are adjusting the learning rate value based on the impact of the variable on objective function or objective function sensitivity with respect to a particular variable. We are updating the learning rate. Okay, then. So that means we are updating, we are adaptively adjusted. The learning rate will be adaptively adjusted, not fixed. The learning rate will be adaptively adjusted based on the impact or sensitivity of the objective function with respect to the a particular variable M or C. Because we have the two model parameters M and C only. So what is the impact of this M? What is the sensitivity of your error function with respect to the M? What is the sensitivity of your error function with respect to C? Based on that one, your learning rate will be updated, not it is fixed during the iterative process. So that is required actually. It's not good to keep your learning process constant. Okay. So about this one, we will discuss further in detail in the last day, that is tomorrow. We will discuss about all the things. And tomorrow, so this is from my side. So if you have any questions, you can ask now.